So I just wanted to cover these Edpuzzle quizzes. This is for this equation. Remember, these two terms are either with each other or they can be like against each other. You know, they could be favorable or unfavorable. All right, so let's go through this. So you're supposed to predict the signs and then figure out what delta G would be as a result. So we have carbon dioxide. It's a solid. So this is dry ice, which is a solid carbon dioxide, and it sublimes at room temperature. So that means heat energy needs to go into the intermolecular forces. So there's a London dispersion force. This is nonpolar. That's what holds it together as a solid. So for it to become a gas, heat has to go into those to separate these two. Okay. So when that happens, the what's the sign for entropy when that happens? So positive, because as you can see, this is more ordered in the solid state, and they'd be free roaming gases, which would increase microstates and disorder. So that means entropy would be positive. So the prediction for free energy would be that this term is favorable, but the fact that it requires heat to do that is unfavorable. So you want this term to win, which it will at high temperatures. So here's our equation. A high temperature and a positive number here will result in this term beating this term. And that's described here. All right, this is the other form. So similar, we're similar concept. We're trying to figure out this term versus this term and apply this this negative here. All right, so we have solid silver. Here's kind of like a picture of what's happening. Solid silver, elemental chlorine, diatomic gas. Okay, those come together. So there's a couple of processes that cause this chloride to become a negative and the silver a positive. So you could review your notes, but eventually the reactants kind of look like this, right? And then they all come together and make a really strong, tight ionic bond. Okay, so that's should be huge in exothermic. So when ionic bonds form, that should be highly exothermic. So this is negative. And like I was saying, it's a combination of several other steps. To see more detail on this, you could check your notes. So basically, this turns into this, right? And then they come together. All right. So enthalpy is negative, so that's favorable. How about entropy? As you can see, it starts off like that, then it turns into this, and then it turns into this. So it's super ordered. So that's negative. And you can see that from you had another way to tell is a mole of gas, and you had like this highly organized solid. So this is favorable. This is unfavorable. When would it be spontaneous? At low enough temperatures. So that would mean this whole term becomes positive since that's negative. So you want the negative enthalpy to beat that, which would happen at low temperatures. This is the second Edpuzzle quiz. This is on this. If you ever see this equation and you want to explain the concept, or you want to try to explain what's going on with this equation, try to think of this curve. I'll try to go through these two scenarios and relate it to this curve. So delta G non-standard, an engineer would be interested in this number because standard confines you to certain conditions. So say you want to, this is the Haber process. Say you want to push it forward, right? So you have to know how to manipulate Q to push this forward and make the desired product. So this with the degree symbol confines you to normal conditions. So that's what an engineer would want this to know the value of delta G non-standard. What do I need to do to push it forward? All right, so here's this reaction. So here it is, the non-standard value. So we plug it in here. And you can see the partial pressure of the product is 8. That's ammonia. And the two reactants are 0.25 and 0.10 respectively. So these are really, really low, and this is really high. And what we know about Le Chatelier's principle is when this is getting super high and these are getting really low, you'll get to a point where it'll start to go this way. So what's happening here is under standard conditions, it's negative 33, the free energy, kilojoules per mole. So on this curve, that means you're like pretty high up here. However, once this reaction starts going left to right, so under standard state, this should go left to right spontaneously. That's what this says. That's if these were all ones. Standard state is 1 ATM, 1 ATM, 1 ATM. So Q would be 1. Okay, so that would be at standard state. So what happens if, what you should notice about this problem is the product is super high. The partial pressure, this is already really high, and the two reactants are super low. So that would suggest it would be less spontaneous, and that's what we see with the value here. So, and you could take a look at Q. It's this giant number. Okay, and that's causing this whole term to be more positive in contrast to delta G when they were all 1 ATM. Okay, so as you build up product, it gets less and less spontaneous. So as you build up product, you're moving down and down this curve. And you'll get eventually to a point where this term would be equal to this term, the delta G at standard. Equal and opposite in sign, I mean. And delta G non-standard would be 0, which is this point right here. Okay, and all that means is the physical chemistry explanation is the free energy of the products are equal to, like if you set this to 0, that means this number is equal to this number. The reaction is, you could think of it as being at its most stable state, the reactants and products, when they are in those amounts. And again, it's, as we know from equilibrium, it's not the amounts don't have to be equal. It's just the free energy is what's equal. All right. So a little bit, if the product were a little bit more and this were a little bit lower, this would be closer and closer to 0. Okay, so you're almost right here. So it takes, as you can see, it takes a lot. You'd have to have this number real high and these real low for the standard state free energy to be 0. And that's what this is describing, this sentence here. So as products increase during a reaction, Q gets larger, the reaction becomes less spontaneous. So it's getting less and less negative as delta G non-standard gets to 0. So here's another good, to look at the other form of this quiz. We could see that what happens when this number is increased. So you could see the two reactants, 0.1 and 0.1. So this is 0.1, 0.1. But the product was changed to 12. So if we look at over here, this was 8. This was 0.25 and 0.1. So this amount was higher and this amount was a little bit lower, right? So Q was a little bit lower. So, but those amounts change in this reaction. So Q actually got bigger because this is bigger, these are lower. And so we got so this RT, ln of Q got so big and positive, it actually was more positive than this. So that means the reaction under standard state would be like up here. But in this case, we have the products and products so high, reactants so low, that you're actually like over here on this side of this U-shaped curve. So, and if you made this even higher and these even lower, then you'd be even higher up here and less spontaneous in the forward direction. Okay, so over time, as this one goes left to right, this reaction would go right to left and make the reactants until it got to this point. So delta G, it's good to think of like conceptually this curve. And so when Q is large, much larger than K, you'd be like up here and reaction shifts left. And if Q is real small compared to K, the smaller it is and the lesser it is than K, the higher up this curve you are. Okay, and as reaction starts going left to right, you get more and more product, less and less reactant, and then you eventually get to 0. Okay, hope this helped.